Is it okay today?
Oh yeah, just a little bit.
A little wet, yeah. I do okay on the quiz? Yes and no, maybe?
No, I can honestly say I did as I expected. How's that?
Okay, well the quizzes are low stakes, so they're not like a big full-blown exam. They're only 25 points, so if you did poorly on this one, that's okay. We can still recover from that. It's not a huge part of your grade, but it is a nice little place to practice on for the exam, which is coming up soon. All right, so I'm just going to go through each of these quickly and work through them. So these are all from past exams, so you can dig back through the past exams and find them. So first of all, for the mattress, a twin mattress is usually 6 feet by 3 feet-ish or so, or 2 meters by 1 meter. So it has an area of 2 meters squared. None of these others are really reasonable. Here, to find the units of S, I would solve for S. Let me show you how to solve for S. To solve for S, I'm going to multiply both sides by A over X. That gets rid of this. A over X. So S is equal to AX over TV. A is meters per second squared. I'm sorry, did I say AX over TV? A times T over X times V. So there's my A. T is seconds. I'm going to put it over 1. X is meters, right? It is 1 over meters. And V is meters per second. So I have 1 over meters per second, which is going to be the same as seconds per meter. So here I can cancel this and this, this, and this, and I'm left with just 1 over meters. So B is the right answer for number 2. Number 3 is dimensional analysis again. So are these dimensionally correct? Meters per second. V naught is also meters per second, plus meters per second squared times seconds. That cancels with that, and I get meters per second on all 3 of those additive terms, so that one's dimensionally correct. By the way, as I do that, I can get rid of this answer and that answer, okay? On this next one, notice I can cancel out an M, I can cancel out one of those X's, and I can cancel out this, leaving V squared. So I'm left with A meters per second squared equals V squared, that's meters per second, squared, because the whole thing is squared, times 1 over meters. That cancels with that, and I'm left with meters per second squared. So this one is also dimensionally correct. So that gets rid of D. And now I look at this last one. My meters cancel. I forget about the half, and I just have V equals A over X. Meters per second equals meters per second squared. X is 1 over meters, or rather 1 over X is 1 over meters. That cancels, not dimensionally correct. So only 1 and 2 are dimensionally correct. All right, how many sig figs? I have 1. I have 1, 2, 3, 4, 5, 6. I have 1, 5, and 4. 1, 6, 1, 5, 4. That's this one right here, C. How many sig figs in this one? I'm not going to do the actual calculation, but I know if I can just estimate. I don't have to estimate it. If I do that with proper sig figs, it's going to be 120. I'm pretty sure that's right. Point is, I'm going to have 2 sig figs in that top number. Yeah, of course, that's right. And then in the bottom, I'll have like 99 or, yeah, I think 99. So I have 2 sig figs on the bottom and 2 sig figs on the top, so I'm going to have 2 sig figs in the final answer. Standard for the second is based on cesium atom to vibrate. X, if I want to know X, I say X squared plus 4 squared equals 5 squared, and I solve that for X. Or you can just realize, hey, this is one of my special triangles, my 3, 4, 5 triangle, and that's 3. By the way, if I'm going to solve this, I would get X equals the square root of 25 minus 16, which is the square root of 9, or 3. And then if I want to know the angle theta, since I know opposite and hypotenuse, OH, that's sine of theta equals 4 divided by 5. So the theta is the inverse sine of 4 divided by 5. Put that in your calculator, and you would get 53 or 50 degrees. You should know this triangle anyway, though. I would just try to commit it to memory because I use it a lot. This is 37 degrees. This is 53 degrees. Okay? Just know that triangle. I use it a lot. And acceleration here, there actually was a mistake here. Most people got this question right. There's an extra 0 in that. If you ever encounter something like that, feel free to ask me in class, but I don't think it impeded anybody from getting it right that knew how to do it. Gosh, there's another mistake. There should be a space right there. So 12 meters per second squared. I want to convert the seconds to hours. In 1 hour, there are 3,600 seconds. But I have to square that term. That was probably where, if you made a mistake, that's probably where you made it. And then meters to miles, or other miles. Yeah, meters to miles. So 1609 down here. And 1 mile. To cancel out the meters here, cancel out the seconds squared here, and leave me miles per hour squared. Oops, not D. Sorry. The answer is 97,000. And then how many centimeters in a kilometer? 1 kilometer times, I want to convert this into centimeters. In 1 kilometer, there are 1,000 meters. In 1 meter, there are 100 centimeters. Or you could say in 1 centimeter, there are 10 to the minus 2 meters. And that's, 1, 2, 3, 4, 5 zeros. That's 100,000. I just counted the zeros, right, to figure out what that product is. Okay? There was another mistake here, but it doesn't impact the answer. Notice C and D are the same. So I'm sorry about that. That was 3 errors on my quiz, but none of them should have really impeded you from getting the right answers. Okay? What are you going to do well in the next quiz? Practice the old exams. All these questions are questions that you should have worked. Or you saw them, you should have had them. And that'll be true on quiz number 2 as well. Those quizzes, while I say they're low stakes, they are important because they add up to equal an exam. So in effect, you have 6 exams. 6 exams. You have the 4 in-class exams. You have the final, which is really like 1.5 exams. And then you have the 4 quizzes, which make up a whole exam. And I'd love for those 4 quizzes to be a solid A for you, all added up together. Okay? All right. We can look back at some of that stuff, but I'd rather move on to Chapter 2 stuff that has to do with kinematics and maybe interpreting plots, and then we can get a little bit into stuff that we're not yet on in the class. But are there particular things that you're itching to talk about today? No? Okay. Let's see. I want to do some of these graphing problems. Like, let's see, this exam has a number of graphing problems, some of which are quantitative and some of which are qualitative. It looks like I have 4 or 5 problems that were actually calculations from graphs. So let's look at those first, because we've been doing that in class. This is fall 20, the exam 1. And here I have, let's see, that's not a good one. Let's review. Okay, so let's look at number 22. We've really just started looking at acceleration. Acceleration, average acceleration, presented that last time as delta V over delta T, and it is the slope of a V versus T graph. So the slope of a V versus T graph is equal to the acceleration. And similarly, as we had a distinction between average and instantaneous velocity, we'll have the same distinction between average and instantaneous acceleration. That is, to find average acceleration, we take 2 points, and we say, what is the difference between those 2 points? For instantaneous acceleration, we take a single point, we draw a tangent line to that point on the graph, and we say, what is the slope of that tangent line? So the same will apply here, whether we're doing acceleration or velocity, average or instantaneous. Here I want to know, on number 22, what is the acceleration at t equals 4.5 seconds? Now sometimes on these, finding the tangent line will be really easy. Like for example, on this one, it is really easy because this is a straight line, and so the tangent line is just the line that that point sits on. Okay? It's a little more difficult when you're dealing with a curved graph. We'll look at some of those in a bit. So here I want to know the acceleration. Acceleration is v divided by t, or delta v divided by delta t. So it's really just the slope of this line. My velocity, which is on the y-axis, is going to have a rise of 0 minus 4, 0, 4, 0 minus 4, and then my run is 5 minus 4. So it's negative 4 over 1, or negative 4 meters per second squared. The slope of that line is negative 4. Now, mistakes that people make commonly, we saw these in class, and a number of y'all made this mistake, is that one, you don't recognize that this is a negative slope, but that line does have a negative slope. And two, when you're finding rise over run, you might say that it's 4 divided by 2, because you're just counting those squares and not paying attention to the units on these axes. It's not 4 divided by 2. In fact, it's 4 divided by 1. So negative 4 divided by 1. Okay? So a lot of students, when they're working this problem, they will put this answer or they'll put this answer, both of which are wrong. All right, let's look at this one. This one has average acceleration, which we're going to do next time in class. But again, it's the same as average velocity. Use the same process. Between t equal 1 and t equal 4 seconds. So I'm going the average acceleration between these 2 points. I don't draw a tangent line here. You don't even really need to draw a line at all, but I like to draw a line that's just connecting the 2 points, and then realizing that I want to know the slope of that line. Or I can say my average is delta v divided by delta t. That's going to be 4 minus 3 divided by 4 minus 1. So that's 1 meter per second divided by 3 seconds. That is 1/3 meter per second squared. So it's going to be D is the right answer. 1 divided by 3 is 0.33. We haven't seen this yet, but we're going to see it tomorrow. Let's look at number 21 while we're here. Let me summarize our graphs first. So x versus t, if I have position versus time, the slope is equal to what? If I have a position versus time, the slope, which is rise over run, which would be delta x over delta t, the slope represents what? Wait, it's what? No, it's position divided by time. That's going to be like meters over seconds. What is that? Right, that's velocity. So the slope represents the velocity. If I have a v versus t, this is why you said acceleration, because the slope of this is what we've been doing, right? This is equivalent to our acceleration. There's something else that we can do with the v versus t graph, and that is to find the area. And the area, well, let's look at slope. Slope is equivalent to delta v over delta t. That is meters per second divided by seconds, which is meters per second squared. But if I'm taking the area of this graph, what I'm doing is I'm multiplying v times t. Right, because if I want to know the area of, say, a rectangle, I multiply one side by the other side, and that finds the area. So if I'm finding the area, say, of this section, I'm multiplying the velocity times the time. And so what are the units of that? Well, that's meters per second times seconds. Those cancel, and that leaves me with meters. So the area of a velocity versus time graph is equal to my we're going to say distance for now, is equal to our distance traveled. So here, up in this problem, number 21, I want to know the distance the object has traveled at t equals 3.0 seconds. So that's right here. So really what I'm asking is, what is the area under this graph all the way over to here? What is the area? You're definitely going to have one of these on your test. Not on the next quiz, but on the next test. The way you do this, the easiest way, is to figure out how much does each square count for? Like, what is the area of each square? So this square, for example, has an area of 0.5. You'll see how I got that? This side is 1 unit long. This side is 0.5 units long. So each square, rectangle in this case, has a value, an area of 0.5 meters. I say meters because it represents a distance traveled. So the area is 0.5. And then let's count those squares. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to combine this one and this one to make 13, this one and this one to make 14, this one and this one to make 15, and this one and this one to make 16. So the answer then is 16 meters. Y'all see how I added up the partial rectangles? Like, for example, I combined this one, which was missing this little amount over here, and I said, let's combine it with this one, and that makes a full rectangle. Y'all see that, how I did that? Yeah, you're going to have to do the same. And, you know, if you get it wrong, well, let me take it back. The answers will be distinct enough. See, there aren't really any answers that are close to 16. You'd have to really botch it up to get an answer of 12 meters. Probably you'll mess it up just because you're doing it incorrectly. Okay? Let's look at some other graphing problems. Let's go. Oh no, let's look at this one over here. So this is number 24 on fall 20. Here I want to know, at which time period does the object have the slowest speed? In an x versus t graph, how do I get the speed? The speed is equal to what quantity from the graph? It's either slope or area. Which is it, slope or area? The speed or the velocity is equal to the, rhymes with Pope, I guess? Rhymes with Pope? The slope, yeah, so the speed is equal to the slope. So I want to look for the place where it has the smallest slope. And the speed thing is relevant because this graph has negative slopes in some point and positive slopes in others, and I don't really care if it's positive or negative because that gives the direction. Speed is a scalar quantity, so I don't care about the direction. I'm just looking for the part that has the shallowest slope. There are 4 segments here, 0 to 1, 1 to 3, 3 to 4, and 4 to 5 seconds. The one with the shallowest slope appears to me to be this one right here. You'll see how it's shallower than all the others? And so the answer then would be 1 to 3 seconds. That the smallest slope is at 1 to 3 seconds. And we can find the velocity there. It's going to be delta x over delta t. This is the average velocity over 1 to 3 seconds, but since it's linear, it's also the instantaneous velocity all along that time interval. Because the slope doesn't change, the average is equal to the instantaneous. So delta x over delta t, that's minus 1. That is 3 minus 4, divided by 3 minus 1, or 2 seconds. That's minus 0.5 meters per second. That's the slowest speed. In comparison, say for this segment right here, I have a speed of 4 meters per second, or negative 4 meters per second. So that's the highest speed at 4 meters per second. That's also the same from 0 to 1 seconds. Okay? Yeah, Carly? Of course. Yeah. Oh yeah, you're right. I counted 16 squares, so the answer isn't 16, is it? What is it? You're right. Look at you. Whew, you gotta be careful on these tests. They're not meant to be tricky, but they're meant to assess your mastery. Okay? Thank you. Yes, be careful, okay? All right. I'm glad I'm not taking the test. No, I'm joking. That's mean, isn't it? No, but be careful. You do have to be really careful on these exams. But it's not that I'm trying to trick you. It's just I want to make sure that you're careful, like you were, obviously. Right? Yes. Okay. Don't worry about vectors right now. We're going to get into that soon. Hopefully it'll be on exam 1. Let's see if we have some more graphing. So there will be some graphing problems that are qualitative too. We've mainly done quantitative. Gosh, I mean, you're looking at probably a third of your next exam is going to be graphing problems when we combine our qualitative and quantitative ones. So you really need to know this well. Fortunately, the next lab that we're doing, lab number 3, will deal a lot with graphing, so I think it will help you to think about it more. Let's look at this number 16. So here I have a graph that is a position versus time graph. It's one-dimensional. It's the x position. So I'm only looking at the motion of an object as it moves in the x direction, either plus or minus x direction. First of all, I can see the places where it's moving in the positive x direction. That's right here and right here, because it has positive velocities. That means it's moving in the plus x direction. And then in the negative direction, it's moving here and here. It has a negative x direction, because the slopes are negative there. I can also see where it's speeding up or slowing down. Let's take each of these statements, 1 through 4, and see which ones of them are true and which ones are false. So between points B and C, I want to know, is the object increasing its speed? So I'm going to draw the tangent line at point B and the tangent line at point C. And the statement says that it's increasing its speed between B and C. What is the speed at point B? It's the slope of the tangent line. The slope of that line is what? It's 0. It's a horizontal line. So right here, the speed is 0. Also at point C, the speed is 0. That means that this object is not increasing its speed. In fact, it starts at 0, then it gets steep, like the slope of that line gets steep, but then it goes back to 0. So it's traveling, it has 0 speed, it speeds up, and then it slows down again, and then it stops between B and C. So this first statement is not entirely true. It does increase its speed, but then it slows down again. Do you have a question, Brian? You look like you're thinking about a question.
No, you could have my head with the whole class. Don't worry about that.
Okay. It's going to be okay. The object is increasing its speed between B and C? No?
I guess the question then would be, what is the line representing? Just connecting points, or?
The line that's drawn on the graph? No, it's asking, as the object moves from point B on the graph to point C on the graph, that is from an x position of 20 to an x position of whatever that is, 7 or 8 or whatever, what is that object doing? And since it's at a 0 speed at B and a 0 speed at C, that means that it has to speed up and then slow down again. It doesn't increase its speed the entire time. All right, so that one's not right. The object has a negative acceleration at E. That one's true, but I don't want to get into it right now, so let's just skip over that. The object is at rest at D. Is that true? The tangent line has a slope of that. Is it at rest there? Right, it's moving. It has a positive velocity. So that one's not right. The object has traveled a total distance of 5 meters at 5 seconds. Well, I can do like we did before, where I look at each individual square, and each individual square appears to have a value of 5 meters. Actually, no, never mind. I can't do that, right? Because this is not a velocity versus time graph. This is a position versus time graph. So has the object traveled a total distance of 5 meters at 5 seconds? That statement has a lot packed into it. You think it has? Let me remind you of the dog question that we had. Remember we had the dog, you're out walking your dog, and you travel from this point to this point. Say you travel from 0 to 5 meters. That's you. But then your dog, on the other hand, runs off here after a squirrel, comes back, and then winds up at the same spot as you. You've traveled a distance and a displacement of 5 meters, correct? Your displacement is 5 minus 0, and then your total distance happens to be the same distance because you traveled straight from 0 to 5. Your dog has a displacement that's also 5 meters, same initial and final positions as you. But has your dog traveled a farther distance than 5 meters? Sure, he's traveled a lot farther, 2, 3, 4 times what you've traveled. That's sort of like in this problem. So here, you're starting at 0, and you stop at a position of 5 meters. I get that value from right here. Your initial and your final positions are 0 and 5 meters. But it hasn't been a straight line path between that because you've traveled up to 20 meters, you've traveled down to 15 meters, you've traveled up to 45 or 40 meters. So have you traveled a total distance of 5 meters at t equal 5 seconds? You've traveled much farther. Now, if this instead said displacement, it would be a true statement that in fact at t equal 5 seconds, your displacement has been 5 meters because your final position is 5, your initial position is 0. Whew, that's a tricky one. So the answer here is 2 only. None of those others are true. A is the right answer. Don't worry about that 2. We'll look at it in a different question. It's a little more complicated here than I want to get into. These are tough questions. They take a lot of practice, and they require you to have a good mastery and a good understanding of how objects move and how we represent them with graphs. Number 18 is a good one. We're going to do this in class, I think, tomorrow. I have this position versus time graph, and I want you to tell me which velocity versus time graph represents the same motion. Now, the slope of this graph equals the velocity. Right? Position versus time, the slope is the velocity. Tell me about the slope right here. Is it big or small, the slope, compared to the rest of the graph? Big or small slope? Big slope, because it's really steep, right? As opposed to over here, where it gets small. Is the slope positive or negative along this graph? Positive. So I have a positive slope, big here, positive slope, small here. So first of all, I'm dealing with positive slopes. And I would get rid of this one and this one. See, because each individual point along these graphs represents the slope at a particular point on the position versus time graph. So I can get rid of A and D because they both have negative slopes or negative velocities. Which do you think is true then, B or C, as being the V versus T graph that represents the X versus T plot, the same motion? Well, I'm starting out with a big slope right here. That means I should start out with a big velocity that's positive, and I should end with a small slope or a small velocity. So which one is that, B or C? About it, commit. C is the right answer. Look, big velocity to represent my big slope, small velocity to represent my small slope. The slope is the velocity. That's a good basic idea of how to interpret these graphs. And if you master these, the other one that we just did, which I know probably seemed impossible to some of you, like number 16, those will seem easier as we move along. Let's do another one that's similar. You have a question? Okay. These are like ones that we've done already. Now let's look at some other exams. We'll come back to that one. Fall 17. Yeah, so let's look at, this is fall 17. Let's look at number 18. Number 18 says you drop an object. That means this is the ground. I have an object up here, and I let it go. Initially, it's going to have a velocity equal to 0. And then at the end of its trajectory, it's going to have a big negative velocity, right? Because it's a velocity in the downward direction. We're catching it just before it hits the ground, okay? So initially it has 0 velocity, and then it has a big negative velocity just before it hits the ground. That's the segment that we're looking at. Well, which graph shows a 0 velocity initially? Only 2 of them show a 0 velocity initially, and which are those? I'm looking for one that has a very small slope. See here, this has a small slope, whereas this one has a big slope, a big steep slope. So I can get rid of this one and this one. It can't be either one of those. So now, both of these graphs start with small velocities and end with small speeds and end with big speeds. Small slopes followed by big slopes. Which one's the right answer? A or C, and why? Well, you're looking for one that represents a negative velocity. What do you think that's going to be?
Oh, so it could be C.
It has to be C, right. Awesome. See, I have a negative slope. Negative slope is small initially, big at the end. Let's go back to this question. Oh, wait, no, sorry. All right, this is fall 18. Yeah, fall 18, number 20. I think this is the first thing we do when we get back on Friday. What is the sign of the acceleration of this particle? I'm going to give you some rules tomorrow that'll look something like this. If the velocity and acceleration are in the same direction, it's increasing speed. Okay? I'm going to draw them as vectors. So if the velocity is in this direction and my acceleration is also in this direction, it's speeding up. A good example of that is if I drop my keys, they're going to be going downward. They're also going to be accelerating downward, and so they speed up as they travel down. Alternatively, if V and A are in opposite directions, that object is slowing down. Okay? A good example of that, or let me draw it graphically. If this is V, if A is in the opposite direction, that means that this object is slowing. So, a good example of that is if I throw my keys up in the air, the first part of that trajectory, as I throw them up in the air, initially they have a big positive velocity. They keep going up, 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 slowing down because the acceleration is down. Velocity's up, acceleration is down, and so they're slowing in speed. And so here I'm asking, does this object, represented by this graph, have a positive, 0, or negative acceleration? Well, let's try to describe this graph in words, or the motion of this object in words. Is it speeding up or slowing down? I look at my slopes. They're small at first, big at last. Is that speeding up or slowing down? It is an object that is speeding up. That means if it's speeding up, that my velocity and acceleration have to be in the same direction. So whatever the direction of my velocity is, that will also be the direction of my acceleration. What is the direction of my velocity? Is it positive or negative? It's negative. So it's speeding up. It has a negative velocity. That means it has a negative acceleration. So C is the right answer. If it were to have zero acceleration, x versus t could look a number of ways. It could look like this. It could look like this. It could look like this. It just has to be a straight line. Those objects are not changing speed, so they have zero acceleration. If it were going to be an object with, what was this? An object with positive acceleration, let's see, I'd need, yeah, this would be an example. This is an example, an x versus t graph, of an object with positive acceleration, because it's speeding up and the velocity is positive. Let me ask you this. This one's tricky. Here's x versus t. I'll make sure I draw this right. What is the sign of that acceleration? First of all, is it speeding up or slowing down? Oh, I'm sorry, y'all can't see that, can you? It is slowing down because the slope here is big, the slope here is small. So this is a slowing object. That means that the velocity and acceleration are opposite one another because it's slowing down. Velocity and acceleration in opposite directions. That's what it means to have that's what it means to be slowing down, that your velocity and acceleration are opposite. And so what is the direction of the velocity? Well, I have a negative slope, so I have a negative velocity. That means that I have a positive acceleration. So just because an object is slowing down doesn't mean that it has a negative acceleration. There are lots of cases where I have a slowing object that actually has a positive acceleration. Okay? A good example of that, a slowing object, oh no, that's not a good example, never mind. Forget I said that, okay? We'll talk about that more in class. All right? Particular questions that y'all have? I know I've thrown a lot at you that you're not going to get until tomorrow, so hopefully for y'all tomorrow, this will make more sense, because often students will struggle with these concepts. That's okay. I hope you're struggling with them. Not supposed to be easy. If it was easy, everybody would be doing it, right? And it wouldn't be valuable. So hopefully tomorrow these things will click a little better for y'all. Particular questions? You want to go over more topics? Or are you sort of frazzled right now? Let's hit another one. Okay, good job. Okay, I'll tell you in just a second. Let's do some more of those quantitative ones. This is fall 18. Let's go ahead and do some kinematics. We're going to see these tomorrow. So, like numbers 10 and 11, these are, word problems where we're using the two equations of kinematics. I'm going to go ahead and give them to you now. They're x equals v naught t plus 1/2 at squared. We've actually seen these equations when we've been doing some dimensional analysis. X is position, v naught is initial velocity, t is time, and a is seconds. And then also, we have v equals v naught plus at. I'll show you how to derive these tomorrow. So here I have a commuter. She's backing her car out of the garage with an acceleration of 3 meters per second squared. And I'm asking, how long does it take her to reach a speed of 4 meters per second? So first I just want to write down the things that I know. I know that the acceleration is 3.0 meters per second squared. I don't know if it's positive or negative. It sort of depends on the frame of reference that you choose for this and the coordinates that you assign to it. I'm going to let it be positive for now. Let me show you why. Because I'm going to say that v is also equal to positive 4.00 meters per second. I know that her acceleration and her speed are in the same direction because she has an initial speed of 0. Actually, I can go and write that. She's initially at rest. She gets up to a speed of 4 meters per second, and so her acceleration has to be in the same direction because she's speeding up, because she's going from 0 to 4. So I'm going to let my acceleration just be positive. Really, the only important thing is that the acceleration and the velocity are in the same direction. And here I want to know how long, that is, what is the time required. So I've written down everything that I know, and I've written down what I don't know. This one is a simple one-step problem. I have my equations here. I recommend that when you get your exam, you just write them on the bubble form. You're not going to have an equation sheet yet. There's really just these two equations that you need to know. This, maybe your trig functions. If you don't know those right off, write those things down. So just memorize these equations, put them on a note card, paste them to your bathroom mirror, do whatever you need to do to memorize them over the next week or two. So I have 4 equals 0 plus 3 times t. And I'm solving this for t. T then is equal to 4/3 seconds, or 1.3 seconds. Now, in the next problem, it says that she brakes to a stop in 0.7 seconds. So I'm going to write down everything that I know. That is that t is equal to 0.700 seconds. I want to know what is her initial velocity. I don't know her initial velocity, right? She's coming out. Oh no, actually I do. I know her initial velocity. It's 4 meters per second. That's this speed right here. She's coming out of her garage, backing up. She gets up to a speed of 4 meters per second. I don't know. She sees a little kid running by in her car, and so she slams on the brakes. She wants to stop, and she wants to stop. She does stop in 0.7 seconds. Then what is her deceleration? So this is our V naught. That is her initial speed. Her V final is going to be 0. I'm just going to say V. I'm just going to call that V. And I want to know what is her acceleration. All right. So on this is again a fairly straightforward one-step problem. I would say that V is equal to V naught plus A times T. V is equal to 0. V naught is equal to 4 plus A times 0.7. So A is equal to -4 divided by 0.7. So that should be 5.7, I think. Number 11, let's go check it. Number 11 should be C. Yeah. Okay. So that's equal to -5.7 meters per second squared. Okay, those are kinematics problems, and we're going to get to those tomorrow. You'll have 3-ish probably on your exam. You'll probably have one in the free response too. Remember, as you're preparing for the exam, and we'll do this in class too, but you will have free response questions. So for example, here's a good kinematics problem. We'll work one like this in class. Here's a graphing problem where you have to graph the motion of an object. Here's a graph that you have to determine certain things like the distance or the acceleration like we've been doing. For example, this one, where I'm trying to find the acceleration at t equal 1.75 seconds. I want to know the acceleration right there. So I draw a tangent line and find the rise over the run. The rise is 8. Or -8 actually. The run is 0.5, 2 minus 1.5, and so the approximate acceleration is going to be -16 meters per second squared. And then if I want to know the distance traveled, what do I do to a V versus T to get the distance traveled? Slope or area? Area, thank you. So each of these squares has a value of 2 meters. I said 4 times 0.5 to get that. So that's 2, 4, 6, 8, 10. I'll sort of combine it with that one. 12, combining it with this one. Maybe 12 and a half, 13, maybe. I'd take 12 and a half to 13 meters for that. Okay? So be thinking about your free response. Good news is that before the exam, I'll give you a pretty good idea of exactly what to expect on the free response. And that's a third of your exam that you're coming into, and you know exactly what it's going to be. I'm not going to tell you the numbers. Like I'll tell you you're going to have a kinematics problem, you're going to have a graphing problem similar to this, so you'll have a pretty good idea. And then also on the free response, you're going to love this, you can get partial credit on your free response. So like if you get it exactly right, you'll get full credit. If you get it just mostly right, you'll get half credit, and if you get it all wrong, then you won't get any credit at all. But I find that often students will get, if they know how to do it, but they just make a simple mistake, whereas on a multiple choice, they would have lost all those points. They're actually able to recoup they recoup half those points. Free response is really good for you. It's a lot of work to grade, but it's good for you. The students' grades are higher because of it. Okay, I think that's about all the physics I can take. Okay? I appreciate y'all coming. I know it's a rainy day, and